So hello everyone, I'm Daniele Sensi from Sapienza University of Rome, and before starting presenting this talk, I would like to thank all the co-authors of this paper. This has been a joint effort involving several different universities and as well as companies and supercomputing centers. And this work is about basically benchmarking and understanding what's the state of practice for GPU to GPU communication, and what motivated by several reasons. First and foremost is that systems are getting larger, and nowadays we have systems with hundreds of thousands of GPUs, and thus it's important to understand what kind of the performance that we can expect in such systems. And at the same time, now compute nodes are getting denser, so nowadays it's quite common to have servers with 4 or 8 GPUs on the same node, and this is likely gonna increase in the next few years. And the third reason was that we wanted to assess the maturity of the software stack. So technology is moving fast, and we want to check if the software exploiting this technology is keeping up with that evolution. And for doing that, we considered three systems, three supercomputers in the top 10 of the top 500, trying to cover different architectures, both in terms of intra-node connectivity, but also in terms of inter-node connectivity. So let's say scale up and scale out networks. And the first system we considered is ALPS. Back then was the number 6 in the top 500, and it is based on Grasshopper chips, so NVIDIA H100 GPUs. And each node is composed of 4 GPUs. They are connected in a node-to-all way. So each GPU has a direct connection to another GPU, to NVLink, and the unidirectional bandwidth between any pair of GPU is 1.2 terabits per second. And then each GPU has connectivity on the scale-out network with 200 gigabits per second per direction, using, in this case, HP Crazy Linkshot network and the Dragonfly network topology. So something important to be said is that when we gathered the data, now it was a little bit more than 1 year ago, the system was still in an early access phase. So some of this data now might be different and things might have been improved, but back then it was still kind of it was still not open to the general public. The second system we considered is Leonardo. Back then it was the number 7 in the top 500. Even in this case, it's based on NVIDIA GPUs, a little bit older. These were NVIDIA A100 GPUs. And even in this case, they are connected in a node-to-all way with a little bit lower bandwidth compared to ALPS. And then in this case as well, we have each GPU has its own connectivity to the scale-out network. Now, in this case specifically, each server on Leonardo has 2 NICs. Each NIC has 2 ports, but in this case, for simplicity, we just show the ports and consider them as if they are separate NICs, let's say. In this case, differently from ALPS, the system is based on NVIDIA InfiniBand and employs the Dragonfly Plus network topology. And the last system is Lumi. Lumi is based in this case on AMD GPUs, specifically MI 250X. And the server architecture here is a little bit more complicated. We have this 8 GCD, which stands for graphic compute dice. We can logically see them as 8 separate GPUs. And the connectivity between them is a little bit more intricate. It's not a full all-to-all. I mean, we don't have from each GCD a direct connection to each other GCD. And depending on which pair of GPUs you pick, you have a bandwidth which differ depending on the specific GPUs. And then basically for each pair of GCD, we have a NIC with 200 gigabits per second towards the scale-out network. So Lumi is based again on HP Crazy Linkshot with the Dragonfly topology. So basically, we try to cover different combinations of scale-out and scale-up networks. So we have NVIDIA GPUs with HP Cray network. We have NVIDIA GPUs with NVIDIA network, and we have AMD GPUs with HP Cray network. So these were the systems we analyzed. So what kind of benchmarks did we run there? We consider several things. So the idea is to move data from one GPU to another one and see what happens. And the most trivial solution is to rely on trivial staging. So this is, of course, which means that we copy data from GPU memory to host memory, then we transmit the data from host to host, and then we copy back the data from host memory to GPU memory. This is, of course, something which doesn't make a lot of sense anymore. We just use it as a reference baseline and as an additional check that everyone was working as expected. Then, in the case where the two GPUs are on the same node, we also consider direct device-device copy, also known as peer access, where basically a GPU can read and write to other GPU's memory on the same node. And then we consider CCL libraries like Nickel and Recall, and eventually, of course, GPU-aware MPI. Now, for all of those, I mean, for Nickel, Recall, and MPI, we used the library version suggested by each supercomputing center. So you can find more details in the paper, but if I remember correctly, these were OpenMPI for Leonardo and Cray and Peach for both Lumi and Alps. But you can find the detail about the versions and the backend and all the other details in the paper. So we basically run 4 different classes or families of experiments. So we have intra-node and inter-node, so to stress the scale-out and the scale-up and the scale-out network, and we have point-to-point and collective operations. For collective operations, we mostly run all reduce and all to all. So let's start with the intra-node case. So we have 2 GPUs on the same node, and we want to assess the point-to-point performance. So how much does whether or not we can saturate that bandwidth. So I will start from Alps. So we have on the x-axis the size of the vector we transfer. So this is a classical ping pong test where we send the data back and forth, and we measure how long does it take. And on the y-axis, we have the goodput in gigabit per second. And we put some horizontal dashed lines there, which are basically the expected goodput that we can compute with pen and paper based on the specifics of the system. And we start with the trivial staging. So, of course, as we can imagine, the trivial staging bandwidth is really low because it requires a lot of transfers between GPU and host memory. And so it is bottlenecked by PCI Express and so on. And then we have CCL, which can saturate around 80% of the theoretical peak bandwidth, and the same. It's what happens for GPU-aware MPI. Then we zoom in this. So let me take the laser pointer here. So we basically zoom in this part here in this other plot up there. And we show here the runtime rather than the bandwidth for those small vectors. So this gives us an idea of what happens for small data transfers. And even in this case, the results are kind of coherent with what we show for large data transfers. There is a note to be made here. The line for device to device copy is missing here because at the time of the writing, this was still not enabled on Lumi. As I was mentioning before, this was still in an early access phase, so we don't have that data point specifically. Now, we did the same for Leonardo. So just beware that the y-axis range changes across those plots for readability reasons. And here things get a little bit more interesting, especially we can see that although there is always this performance gain of MPI compared to Nickel for both Alps and Lumi, we can see that this is particularly particularly significant for small messages. So here we have that for vectors between 1 byte and 4 kilobytes, MPI it's up to 10 times faster than Nickel in this case. And specifically here, the reason was that MPI was relying on this small library, which is called GDR copy, which optimizes small data transfers for MPI. And this was the reason why there was this large performance gap. On Lumi, we observed something similar. So we can see that actually the gap between the measured output and the expected output is a little bit higher. I will get back on this later on the reasons why this is the case. But for now, what I want to focus on is that also in this case, we have this kind of large performance improvement of MPI compared to recall, in this case, for small messages. But this is for a different reason. So in this case, both the CPU and the GPU were AMD based, and basically in this case, Cray and Pitch can exploit an optimization by which the CPU can directly load and store, issue load and store instructions to the GPU memory, and this basically allowed Cray and Pitch to reduce the latency by up to 10 times compared to recall. So to sum up for intra-node point-to-point results, so one thing I forgot to say actually is that these were not the first results that we got. So when we start running those benchmarks, the results were quite different from these ones, and we had to do some tuning. So which means that in many cases there were environment variables to be set and things like that that we had to do in order to bring up the performance of those tests. You can find again the details in the paper. Specifically, there were a couple of environment variables that when setting them, basically we were able to get some significant performance improvement. The other result is that we can see that for small point-to-point internal transfers, MPI can be up to 10 times faster than Nickel. And I explained some of the reasons why this is the case. Now, let's move to collective operations. So we are still within a single node. So we are still stressing the scale-up network. And specifically here, I only show the data about the all-reduce. In the paper, there are also results about the all-to-all. And here we can see that the situation is different. So before we had that MPI was always comparable or even better than Nickel. Here is the other way around. So we can see that both Nickel and recall have a large performance gain compared to MPI across all the systems. Now there are many reasons for that, but one of the reasons is that both Nickel and recall are explicitly and very well tuned and optimized for the specific system they are running on. So they basically, when they run, they are able to detect on which model of GPUs they are running and optimize many parameters like how many bytes to keep in flight and things like that in such a way that they can actually saturate the available bandwidth, especially for collective communication. So this was quite consistent across all the three systems, and in some cases this led up to 3x or more performance improvement over MPI. Now, there is a small note to be made. So here specifically on Leonardo, MPI performs really bad for the overreduce. And the reason for that is that on Leonardo, we use OpenMPI. And in this specific case, OpenMPI was performing the actual data aggregation, so the actual sum of the vectors on the CPU rather than on the GPU. So this basically involved a lot of transfers again between the device and host memory. And this was the reason why the MPI performance here is really, why MPI here is really underperforming. So this was an issue related to OpenMPI, and I'm not sure if this has been solved in the meanwhile. Okay, so but here about collective operations on scale-up network, we basically conclude that in this case CCL outperforms MPI up to 2x. Now let's move to the scale-out network. So inter-node communication, specifically point-to-point communication. I'm not going to show you the data here. I'm just going to report the summarized sentence. But what we observed is that even in this case, consistently to what we observed for the intra-node case, we observed MPI outperforming CCL up to between 3 and 10 times, depending on the vector size. I think, but one important result about point-to-point transfer, which is worth be described a little bit more in detail, is related to Leonardo. So at some point, so Leonardo is based on a Dragonfly Plus network, which means that we might expect differences in performance depending on the location of these nodes. So we have two nodes communicating, and now we can decide to have these two nodes under the same network switch, under two different switches in the same Dragonfly Plus group, or even under two different switches in two different Dragonfly groups. So we try to understand what's the impact of the allocation on the performance of node-to-node transfers. And we repeat it for many times, and we plot the distribution as a box plot. So we have, in this box plot, we report several things. Of course, we have the usual first and third quartile, and we have the average and the median. And what we can see here is that as long as the two nodes are under the same switch, everything is smooth, and there is basically no variability in performance, and this can reach the peak bandwidth, which in this case was 400 gigabits per second. But as soon as we move the nodes that are communicating under two different switches, we can see that we have this large performance variability. We have this large performance variability, which eventually let the bandwidth drop by around 25% or 20%. And we observed this also for the latency. So this was something affecting both large message transfers, but also small message transfers. And in some cases here, there were some outliers, increasing the latency up to 4 or 5 times compared to the average case. Now, why this is the case? In a nutshell, so we ran some more detailed experiments to explain why this was happening, and the most reasonable explanation that we can have is that this is due to network congestion, of course, and basically it seems that in its current state, the adaptive routing it's not really working at the best of its possibility, in the sense that it seems that although the issue is mostly when we have two nodes under two different switches in the same Dragonfly group. In this case, the Dragonfly group that we have, it's a full bandwidth Dragonfly group, so there is no tapering. Anyone should be able to talk with anyone else at full bandwidth, but this is not the case, which means that probably there is some congestion, and even if there is available bandwidth, some network flows are sharing the same links, even if this was not strictly necessary. So we don't know if this is a configuration issue or if this is a more fundamental issue, but we ran some more detailed tests to actually prove that this is the case, and you can find that analysis in the paper. Okay. And which means that basically this network congestion or network noise, in this case, increases the average latency up to 2x. And we observed also that for collectives, this leads to performance drop up to 50% at scale. We also ran a similar test on ALPS and LUMI, and we didn't find any significant impact of the allocation on the network performance. Okay, so the last family of experiments involves collectives on the scale-out network, so collectives between multiple nodes. As in the previous case, we report with this kind of horizontal dashed line the expected output. So here in this case, we say that this is the asymptotically expected output in the sense that this is an all-to-all, and for simplicity, we assume that all the communication happens on the scale-out network, which is not necessarily the case because a small fraction of communication happens between GPUs on the same node. But for simplicity, we assume that everything happens on the scale-up network, and this is why we call this asymptotic, which means that for when we run this on a few GPUs, the actual measured bandwidth might be a little bit higher than that. But let's say for a large number, for a large enough number of GPUs, this is what we should expect. And we start from ALPS. So we compare nickel with GPU-aware MPI on ALPS. And there are a couple of things to mention here. The first one is that consistently with what we observed on a single node, the nickel performance is higher than MPI performance. Again, also in this case is because of more aggressive optimizations adopted in nickel compared to MPI. But there is also something else to say. As you can see here, the nickel data points stop at 256 GPUs, and this is because with the higher number of GPUs, nickel was crashing in this case. But again, this system was still in an early access phase, so probably the software stack still needed to be improved or tuned or properly configured. Then we run a similar experiment also on Leonardo and Lumi. This is still consistent with what we observe for ALPS. So there is always this kind of big performance gap between nickel and MPI. And the same also happened for Lumi. So here the gap is smaller, but we can see again that the recall data point here stops basically at 512 nodes. And again, the reason for that is that when running with more than 512 GPUs, recall was deadlocking. We found confirmation of that. Also, there was an issue on GitHub mentioning that, but apparently this specific version of recall had a bug by which basically with a high enough number of GPUs, eventually this was feeding to a deadlock. So we were not able to gather data with more than 512 GPUs. So the conclusion we got from this test is that on large-scale collectives, it seems that CCL, both nickel and recall, outperform MPI. However, we observe some instabilities. So, but again, it's important to remark that this was data collected in March 2024. So I guess that in the meanwhile, some of these things might have been addressed. The very last plot is about trying to understand more what's this relationship between MPI and nickel. Sorry, in this case, MPI and recall. So this was done on Lumi. And in this case, we show basically the performance ratio between recall and MPI for different numbers of GPUs and for different message sizes. And now, regardless of the specific numbers, the important point here is that there is no a single solution always being the better overall, in the sense that specifically in this case, we can see that for smaller transfers, MPI is usually performs better than recall up to 1 order of magnitude, but for larger vectors, it's the other way. So this kind of shows that there are opportunities for improvement on the software side on both sides, and that so far none of them it's ideal. Okay, so let me conclude and basically wrap up the discussion with some let's say take-home messages. So the first one is directed towards users and system administrators, and is that especially for the point-to-point experiments, we found that there was some non-negligible tuning effort required to achieve good performance. Again, this is discussed more in detail in the paper, but there are many moving parts, many parameters that can be specified both on nickel and MPI, which in some cases might have a large impact on the performance. The other point is about this comparison between MPI and nickel or equal. And it's not clear. I mean, so far it seems that there is not one framework always be better than the other one in all the situations. This depends on whether you are running point-to-point operations or whether you are running collective operations, on how large your vector is, on how many GPUs are you running this. So it seems that there is a lot of space for improvement on the software side on both sides. And the last point is it's more about, let's say, network architecture. It seems that adaptive routing, at least on the system we use, might require further optimization. Again, we are not sure if this is a configuration issue or a design issue, but this is what emerges from the data, and so some additional investigation might be done in that sense. Okay, so this concludes my talk. Thank you for listening.